This is Walter Leite, and in this presentation I will talk about neural networks to estimate propensity scores. So, neural networks consists of a large number of connected neurons that are organized into three layers: the input layer, multiple hidden layers, and an output layer. This can be shown in a graph where the neurons are the nodes and the edges are the connections between neurons. Here the edges are the arrows. Now there is also a bias that's added that's like an intercept of one, and the edges correspond to weights that weight the components to provide an output for each neuron. So a neuron, also known as a perceptron, is a scalar function, so it outputs just a single number and combines inputs with weights and a bias. Okay, so here you can see that there could be multiple inputs that are combined with weights. So in machine learning, like each feature is an input. So for propensity score estimation, the features are the covariates that you want to balance, and so each covariate is an input and it's weighted to provide an output. Now, if you have a single neuron, so a single perceptron, there can be just a simple learning rule to find the weights, and it's based on starting all the weights at 0 and iterating until all instances are classified correctly. So in case of propensity score analysis, it will be classified into treated or control cases, and you would iteratively adjust the weights until classification, treatment, and control groups are correctly. Now this is for one perceptron, which in most cases for neural networks we have multiple perceptrons, not a single one. Okay, so the single layer perceptrons can deal with simple problems, and here are some examples. So in the first graph, the top left, we have two attributes. So think about two covariates, one in the x-axis and the other one in the y-axis. And the black dot is the classification of 1, the empty dot is classification of 0. So in this case, the observation is classified as 1 if attribute A1 is 1 and attribute A2 is also 1. So these perceptron with the weight shown can provide correct classification. For the second one, it's a OR relationship. So if attribute 1 is 1 or attribute 2 is 1, then the class is 1, which you can think of class equals 1 is like treated, okay, for propensity scores estimation. Now the AND relationship or OR relationship can be handled by a single layer perceptron, but in more complex cases you need a multi-layer perceptron. This is the case where this is an example where it's an XOR relationship, which means the class is 1 if exactly one of the attributes is equals to 1. Okay, and in this case, you can't use just a single layer perceptron. You would need 3 here. A and B receive input directly from the data, and then perceptron C receives input from perceptrons A and B. So here there are two hidden layers. This will be the example of a neural network with two hidden layers. Now, how do you learn the weights? I mean, there are two important tasks for training a multilayer perceptron. You have to learn the structure of the perceptron and learn the weights. The method that's used is called backpropagation, and it consists of modifying the weights interactively to optimize prediction using a method that's used a lot in optimization called gradient descent. So gradient descent, it requires that you have the function you optimize is differentiable. So here we have you can have multiple different functions as long as you can get the first derivative of it's fine. Here a common loss function that is minimized in neural networks is the squared error, but there are others that too. Now you need an activation function for the hidden layers as well as the output layer. So the activation function is a transformation that a neuron uses to change the weighted inputs from other neurons into a prediction or output. So these are some examples where you have the graph for it, the sigmoid, tan, and soft plus, the actual function, and the derivative that's used for gradient descent. Now, you need two activation functions for a neural network. You need to set up an activation function for the hidden layers and another for the output layer. For the hidden layers, the ReLU activation function, which is very simple, it just returns either 0 or X. So if the value is negative, it returns 0. If it's positive, it returns the value itself. That's used a lot for the hidden layers. Now, for the output layers, the choice of the activation function depends on the prediction desired, because the output layer actually produces a prediction. If it's the neural network is to predict a continuous outcome, linear activation is used, which means no activation. It just returns the value untransformed and is continuous. If it's a prediction of a binary outcome, the sigmoid activation, which is the logistic function, is used because it returns a value between 0 and 1 that can be interpreted as a probability. If there are multiple discrete variables, such as multiple versions of a treatment, treatment A, treatment B, treatment C, the softmax function is used because it returns multiple values between 0 and 1 that sum to 1, so this would be, like a multinomial logistic regression does. Okay, so here is some pseudocode for neural networks, and this pseudocode shows briefly, how the main steps of a neural network. You need to define the number of iterations, the step size for the sequence, the regularization parameter, which is the learning rate. You also need to define a layered graph, which is how many hidden layers, and what's the activation function. You need to define an activation function for the hidden layers and activation function for the output layer. Okay, then you start choosing weights. they start at random, and then to calculate the weights, you go through a process of back propagation, which is more complex. He just showed us a back propagation function. And to obtain the weights that minimize the loss function. And then you output the best set of weights, which can be used then to obtain predictions. So one implementation of neural networks to estimate propensity scores was proposed by Collier and Leitchi in 2021. They used for the hidden layers, they used the ReLU, the rectified linear unit activation function. For the output, they used softbacks. And the reason here is because their output was multiple treatments. There were 3 different versions of the treatment. So instead of a sigmoid, which would be better for two treatments, here they had 3, so they used softbacks. For training and for the data split, they used 80% for training, 10% for validation, and 10% for testing. The loss function, they use cross entropy, and for learning rate 0.001, and starting with 3 neurons. So the results they obtained, for a treatment with 3 categories. So the types of treatments are teachers being assigned a mentor, new teachers being assigned a mentor, and the 3 types of treatment is no mentor, mentor of the same area, mentor of the other area of the teacher. And they compared 3 ways of obtaining propensity scores with respect to covariate balance. Multinomial logistic regression, which is MLR here, generalized boosted modeling, GBM, and neural networks. And you can see from the last row of the table, which is the maximum value of the standardized mean difference between for each of these groups, they found that the lowest value was for neural networks. So in sum, propensity scores can be estimated with neural networks, and it's possible to outperform logistic regression and other machine learning methods, but it's more difficult to do this with neural networks because one, there are multiple hyperparameters that need to be specified, and neural networks require large training data sets, and tuning these hyperparameters may be time consuming. But it is a promising alternative to other machine learning methods and to logistic regression.